Welcome to Spring LIB.
In each part of this problem, we are told that we have 1 molar of a solution of the given compound at standard conditions, and we want to know which reactions will occur in the cathode and the anode. So since these are all aqueous solutions, if we start with the compound given in part A, which is NiBr2, we know that means that we have Ni2 plus aqueous ions in solution, Br minus aqueous ions in solution, and because this is aqueous, we also have water. And we know that in the cathode, reduction occurs, and in the anode, oxidation occurs. So we need to use the information of those initial ions that we have in order to determine, once we electrolyze this 1 molar solution, which of these half reactions will occur in the cathode and which one will occur in the anode. So we know that we have Ni2 plus. And so based on the standard reduction potentials table with the provided half reactions, we know that Ni2 plus, if we start with that, then we have to add 2 electrons to reduce it to solid nickel. So Ni2 plus can be reduced. And for Br minus, if we look at the half reactions table, we see that we produce Br minus from the reduction of Br2. So therefore, we have to oxidize Br minus to Br2. And we also know that water, H2O, can either be reduced or oxidized. So we have 2 reactions in each case that can either be reduced or oxidized. And so we need to know which one will occur. So again, the 2 half reactions that are above this red line are both reduction reactions, and the 2 below it are both oxidation reactions. And so when we look at the standard reduction potentials, we know that the top 2 represent reductions, and therefore the reaction with the higher value, and in this case, the less negative value for the standard reduction potential, will have a greater potential to be reduced, and therefore will undergo reduction as opposed to the other one. And we can see that negative 0.223 is greater than negative 0.83. And so therefore we can conclude that the first reduction reaction will occur since it has a higher potential to be reduced than the reduction of water. And since that is a reduction reaction, it will take place in the cathode. And now the bottom 2 reactions are the 2 possible oxidations that can occur. We have flipped the signs of the standard reduction potentials after we changed both of the reduction half reactions into oxidation reactions. And so that means that both of these potentials correspond to oxidation potentials. If we write them out as they are given in the table, then those come out to a value of positive 1.23 and positive 1.09. And those would represent the reduction of O2 and Br2 in each case. And we know that if those are both positive as they are given in the table, then 1.23 is greater than positive 1.09. And so that top reaction, the reduction of O2 to form water, would occur over the reduction of Br2 to Br minus because it has a greater standard reduction potential. It has a greater potential to be reduced. But that means that the other reaction, which is the reduction of Br2 to Br minus, since it has a lower positive value for the standard reduction potential, would have a smaller potential to be reduced or a greater potential to be oxidized. So when we flip both of those reduction half reactions to oxidations, we see that we can compare them now, since they are both negative now and represent the oxidation reactions, to see which one is larger. And that will correspond to which one has a greater oxidation potential and therefore will be oxidized. So we see that negative 1.09 is greater than negative 1.23. So either based on the fact that the oxidation of Br minus has a greater potential to be oxidized than water does, or based on the fact that that oxygen has a greater potential to be reduced into water than Br2 has a potential to be reduced into Br minus ions, we can conclude that this is the oxidation reaction that will occur, and we know that oxidation takes place in the anode. So we use that same logic to work through the other parts of this problem. Part B, the aqueous compound we have is AlF3. So that means we have Al3 plus, which will be reduced, and we have F minus ions, which will be oxidized. And again, water can either be reduced or oxidized. So examining those first two half reactions, which are the two possible reductions that can occur, we see that the reduction of water has a greater standard reduction potential than the reduction of Al3 plus. So that means it has a higher potential to be oxidized than the reduction of Al3 plus, or has a higher potential to be reduced. And so it will be reduced. So this is the reaction that will take place in the cathode and undergo reduction. Now the bottom two half reactions both represent oxidations. And so if we compare the two standard reduction potentials, which are both now corresponding to oxidation potentials, we see that the oxidation of water has a higher potential than the oxidation of F minus. And so therefore, the oxidation of water will occur, and oxidation takes place in the anode. Finally, for part C, the compound is MnI2. So we have Mn2 plus and I minus ions in water. The first two reactions represent the reduction half reactions. If we compare their two standard reduction potentials, then we see that the reduction of water has a higher potential to be reduced than the reduction of Mn2 plus, and so therefore water will be reduced. And reduction occurs in the cathode. So that reaction takes place in the cathode. And the bottom two half reactions represent the oxidations that will occur. And so in order to determine which one will proceed, we need to compare their potentials to be oxidized. We see that negative 0.54 is greater than negative 1.23. So therefore, I minus has a greater potential to be oxidized than H2O. And so it will be oxidized, and oxidation occurs in the anode.